Hi, everyone. So today I'm going to talk about how we can use sulfur modeling to assess chemical injection for odor control, but not only odor control, but also investigate how the chemical addition can impact your secondary treatment. So for this project, we used a focus sulfur model within the SUMO modeling package for this work. And I really think this was a good case study because sulfur modeling is widely applied, in the collection system, but not so much at treatment plant. And using that approach, we're able to really get good results and make good recommendation for the client. So I will go through the process of how we developed the model, calibrated the model, and I will share the results for this project. All right, so starting with some background. So this is a project that we did for the TRA cruise plant in Texas. So it's a pretty big plant. It's about 189 MGD. It's a BNR facility. And the reason why we used modeling for this project, there was lots of expansion going on at the plant, at the headworks, also in the solids processing. And actually, during that project, we're kind of we're installing a new THP process plus anaerobic digestion, which made field testing very difficult. And that's one of the reasons why we decided to go with modeling for this project. So we tested three different chemicals: pure oxygen and ferrous sulfate. And the reason for that, so they actually had an oxygen injection system at the headworks that needed to be rehabilitated. And one of the goals of this project was to evaluate if that rehabilitation was justified. And with ferrous sulfate, they've been using that historically in the collection system. And we wanted to also model the impact of ferrous sulfate injection at the plant influent throughout from the raw influent throughout the preliminary treatment and to the primaries. And we also tested magnesium hydroxide, and I'll share the results later. So like I mentioned, this project, beyond H2S mitigation, we also looked at the impact on the plant process as well. All right, going to the model development. So we used the SUMO 2S model, and using the plant data, the focus was really at the front of the plant, from the raw influent through the preliminary treatment and through the primaries. So we added the process volumes to represent the influent facilities, and we calibrated the model at different airflows so we can cover the flows that was coming into the plant. So historically, they have piloted ferrous sulfate injection at a ratio of 2:1. So we calibrated our model with the pilot data. And for oxygen injection, we also used the plant data that we got with a target DO of 11 milligrams per liter at the injection point. So we calibrated our model with that, and with MAC hydroxide, we dose MAC with a target pH of 7.6 and 8 to evaluate the impact on the sulfide levels. All right, so this is for the calibration process. So to go into more detail about the oxygen injection calibration, so the graph that you see on the left, it's basically the DO profile from the pump station through the primaries. So with a target DO of 11 milligrams per liter, we injected about 5,700 pounds per day. And you can see that we have the model output here. And for the plain line, we have the pilot data. So pretty acceptable calibration. And on the right side, as we track the DO profile, we also track the dissolved sulfide profile that you see here on the right. So important key parameters in the model calibration was really the sulfur oxidizing bacteria, where we had to adjust the concentration. But more importantly, because of the turbulence that was happening towards the plant, we had to adjust for that, and we use different airflows to represent that into our model. So moving on to the ferrous sulfate calibration. So as I mentioned, they did a pilot study at the ratio of 2:1 with a 50 mgd influent flow. So using that data, we calibrated our model as well. And as you can see on the right here, we had a pretty good calibration. So something important with the iron addition, we had to watch for the iron sulfide dissolution and precipitation rate to get to that level. I don't have time to go to more details, but that was the two key important parameters for the calibration process. All right, so moving on to the results. So first for pure oxygen, so as I mentioned, we calibrated the model at 4 different flow rates, and that's what you see here. So we targeted 5 milligrams per liter DO at the headworks, and you can see the DO level at the different flow rate here. And as we move towards the plant, we track down the DO profile. As you can see, the levels are going down, which makes sense. And on the right side, you can see how it reflects on the dissolved sulfide removal in comparison to the baseline. So the baseline is the red line. So in general, we're able to find that with the pure oxygen injection, we're getting about 60 to 70% dissolved sulfide removal. But something important to understand is when we add oxygen in the system, what we do, we want to oxidize our sulfide, but we also want to prevent the sulfide from being formed by increasing our the ORP level in the wastewater. So what that does is it allows the sulfur oxidizing bacteria to use the oxygen that you add in the system, but also other bacteria can use that oxygen as well. When these bacteria use the oxygen, they use the VFA, which can be detrimental to your secondary process. And I will talk about that in the next slide. So what we did here, the plant for the secondary treatment, we use an EBPR process, which need a VFA to remove your nutrient. However, if you add the oxygen, you are consuming that VFA. So in the graph that you see here on the left, you can see the VFA profile that is dropping with the oxygen addition in comparison to the baseline, which is no oxygen addition. So on average, we're getting about 10 milligrams per liter, 10 milligrams of VFA reduction. But for this plant, the good thing is they were getting enough VFA coming into the secondary process, about 60 milligrams per liter. And we found that that reduction, that 10 milligrams of VFA reduction will not be detrimental to the nutrient removal process. So in a situation where we have a plant that is limited in VFA, we will be careful with recommending oxygen addition, for example. All right, so moving on to our ferrous sulfate addition. So after calibrating the model of a ratio of 2:1, we also ran the model at a ratio of 3 and a ratio of 4 to see what will be the impact on the sulfide removal. So that's the result that you see here on the right. So this is with ferrous sulfate addition. This is where we got the most sulfide removal, about 70 to 75% dissolved sulfide removal. But something important to note here is that the ferrous sulfide precipitation actually release hydrogen ion into the wastewater, which you are basically consuming alkalinity with the ferrous sulfate addition into the system. And so what we did here, we tracked the alkalinity and the pH levels with the ferrous sulfate addition. So the graph, this graph shows the different dosing rate of iron, and we had the alkalinity demand with the different dosing rate that we model. And on this line also shows the pH. So as you are higher pH, you decrease your, as your pH goes down, you increase your alkalinity demand. So the plant historically have got issues with pH dropping around 6.6. And with that level, we are able to see that, okay, with a dosing rate of 2 and 3, we're pretty good there. But if we increase the dosing rate to 4, we might get to that limit, and that can potentially cause issues for the nutrient removal. All right, so for mag hydroxide, so we know that the sulfide equilibrium in the wastewater is driven by pH. So when we add mag hydroxide, we don't necessarily care about the sulfide in the wastewater, but what is important is to increase your pH. And by increasing your pH, you basically maintain the fraction of sulfide that can go into, you lower the fraction of sulfide that can go to gas phase. So at 4,400 pounds of mag addition per day, we will target a pH of 8. This is the result that we got. So at no addition, about 45% of the sulfide in the wastewater or in the fraction that can go to gas phase. And if we increase that pH to 8, we're able to reduce that 44% fraction down to about 20%. So we're getting close to 50% removal with this approach. But one thing to understand is with mag hydroxide addition, mag helps with increasing your alkalinity in your water. And for the different plants that use secondary treatment, for example, EBPR processes, alkalinity is really important, and it's helped with improving your secondary treatment performance. So if this was a plant that needs more alkalinity, beyond the H2S removal with mag addition, this is also another benefit as well for the secondary treatment. All right, so in summary, we were able to find that all this chemical addition, of course, can help with sulfide reduction in the wastewater. We're getting about 50 to 75% sulfide removal for all of them. And this was a good case study for us to show the benefit of sulfide modeling in treatment plants. And in the second phase for this project, beyond the preliminary treatment through the primaries, we also assessed what was happening in your recycles, in the solids processing as well. So I don't have time to share that, but if someone is interested, I'll be happy to share those results as well. All right, and I'm happy to get questions if I have any questions. Thank you.
Thank you, Ulrich. Great presentation.
Thanks, Inken.
We don't have any questions right now in the chat. If somebody has any questions, please put them in the chat in YouTube. If we don't get any, we do have 5 minutes and no advertising break. I mean, we have a break, but no sponsors. So we do have a little time to dig a little deeper. Oh, here's a question. Thank you, Scott. What about synergies with combining iron and mag hydroxide?
This is a very good question. So, of course, if you combine mag hydroxide with other chemicals, you will get better sulfide reduction. But that's something that we did not model. But for different projects, we kind of look at combining different chemicals depending on the goal, and we have seen better odor removal with this approach of combining chemicals. But for this effort, we did not do that.
Do any of the other moderators have any other questions? I think it's a great example of how we need to look beyond odor control, right? The impacts on the plant, like how when we're treating in the liquid phase, it always has an effect downstream, pH, alkalinity, VFAs. All of that needs to be considered, and sometimes you can get like the dual benefit of odor control and process improvements. So it's really valuable to have that knowledge and dig a little deeper before just choosing one technology. Well, hold on. Any thoughts on whether it's better to use an iron chloride or iron sulfate? It's very specific.
Yeah, it is. It's a good question. I think this depends also on the client preference and the cost, and there's different factors that we need to look at. But looking at some data, I haven't seen any difference in terms of efficiency when we use iron chloride versus iron sulfate.
Well, I just know there's a few clients that have chloride limits, so limiting the amount of chloride that's added to the collection system is helpful for those.
That's
clients.
another factor, yeah. Good point.
Well, Ulrich, do you want to share, like, just a couple of minutes, what the outcome of your of when you were looking at the sludge, how it was affected? Is that something you can do in 2 minutes?
So let's see. I don't have that open right now. But essentially, so in the solids processing for recycle, what we looked at is the precipitation with struvite. So we know that when you add mag in your system and you have digestion, what you do, you can potentially have struvite formation, which is something that you don't want. So we are able to calibrate the model and predict what was the threshold with the mag addition to kind of avoid struvite formation in your solids processing. So I don't have the numbers right now, but this was one of the additional things that we did there.
Yeah, really, really good look, because that's obviously another effect. Negative side effect is this potential struvite formation.
Yeah, specifically when you have anaerobic digestion.
Right.
You want to watch for that.
Right. All right. Well, cool. Well, thank you so much, Ulrich. We'll let you off the hook.
Yeah, thank you.
Appreciate the presentation and insights.